Hi everyone. So today I just wanted to do some examples. So we've proved this classification theorem that says all surfaces that have no holes, have no boundary, and have finite volume are of a particular form. They're either a connected sum of toruses. So torus, cut a disk out, glue it to another torus, cut a disk out, glue it to another torus, etc. So they either look like that, or they're a connected sum of a bunch of RP2s, which I can't draw as well. But at least in the case where there's just two of these, we get the Klein bottle, which we can visualize. Or then there's one simple case that doesn't fall into these categories, which is just the sphere. So that's the theorem. And in the last lecture video, I gave a sketch of the proof, which is that if you have any polygon with edges identified, then there's a sequence of moves which allows you to reduce it to a polygon with edge identifications, which is clearly one of these three types. And by the way, people have asked this, so let me tell you that one way of representing the sphere as a polygon with edges identified is by taking a loon and just gluing the edges together. And of course, if this angle is 360, then you can check that we're actually getting the sphere if both these angles are 360. But if we have something smaller, then it's just topologically equivalent. It can be stretched to the sphere. But this theorem is really just about topological equivalence anyways. It's saying that any surface can be actually stretched to be one of these three. There is, I guess I should add, there is one question, which is, can any surface with no boundary and with finite volume be represented as a polygon with edges identified? And that turns out to be true. It is a fact, but we're not going to prove it in this class. We're just going to assume that our surface comes from a polygon with edge identifications, and given that setup, show that it takes one of these three forms. So today I wanted to talk more about these moves and do some examples to sort of show how this works in action. So I've written down the three main moves from the last lecture video, but I didn't say how we get from point A to point B. So when you're doing this on the homework or on an exam, you're going to want to go back to the previous video and see how you actually get from this setting to this setting. But let me just run through these again. So the first move was if we have a polygon with edge identifications and we see something that looks like an RP2 in the sense that we've got two edges somewhere on this polygon which are glued together with a twist. And remember, this X is just meant to represent a bunch of edges, and this Y is a bunch of edges with a bunch of identifications that I'm not worried about right now. That's why I've got the squiggle lines there. Then there's a cutting and gluing you can do to get to this picture here. And in fact, this one's relatively simple, so I'll just draw it. The cut is right here, and then you glue the red edges together, and that gets glued like that, I guess. But the point is that if you see if you see something that looks like an RP2, except these two red edges aren't adjacent, you can cut along this purple line, glue the red edges together, and then you get something which is clearly coming from a connected sum with an RP2 because these edges here are adjacent. One other thing I want to mention, which I didn't really emphasize in the last video, is you'll notice that if I take these two pieces, the top half and the bottom half, I have to flip the bottom half to glue the red edges together. So this gets glued to that with a flip. And what that means is that any edge on here, which was pointing clockwise, once I flip it and glue it back together, it's now going to be pointing counterclockwise. So all the edges, their direction switches in the sense that if they were clockwise, they become counterclockwise when I glue along the red edge. If they were counterclockwise, they become clockwise. And that's why I wrote this little inverse here. That's just to remind you that if you go from here to here, you have to reverse the direction of all the edges here, and the order actually. But what I would recommend when you're doing these problems is just to carefully do the cutting and gluing and see what pops out over here. Okay, so whenever we see something that looks like an RP2, we can replace it by this figure where we sort of manifestly have an RP2 as part of the connected sum. And the second move was a similar idea, but with a torus. If we see four edges somewhere on our polygon, which are glued in the way of a torus, in the sense that opposite pairs get glued with no twisting, then through a sequence of moves, this one actually takes two cuts at a minimum, we can rearrange things so that we have a piece which really is a connected sum of something with a torus. And there's no, since all these edges that are getting glued don't have twists, we never have to flip things over like we did with this piece. And so actually the order and the direction of the arrows doesn't change for these pieces. And so this is what we end up getting. So that's the second move that allows us to break toruses off. And the third move is kind of special. It's if we have a pair of edges being glued without a twist, so kind of looks like the torus picture, but we don't have that other pair. And in particular, we have to assume that none of the edges of X are getting glued to any of the edges of Y. And if that's the case, then the edges of X themselves form a surface, as do the edges of Y. And you can take just the connected sum of the X and Y, and this red is really just a cylinder between them, which in terms of stretching is the same as just gluing X with a disk removed to Y with a disk removed. And so we can replace this with this, which cuts down on the number of edges. So those are the three basic moves that hopefully can get our polygon into this kind of form. There's one extra step that's required that could get us stuck, which is really what this does is it reduces our polygon to a bunch of toruses and a bunch of RP2s connected sum with each other. And so what you're going to end up with if you do these moves in general is torus, RP2, so some collection of these. And so there's a further reduction that needs to be done to make it just toruses or just RP2s. And so that's kind of a fourth step, which was a homework assignment, which is to show that anytime you see a torus connected sum with RP2, you can just replace it with three RP2s. It's not possible to prove this just from these moves, but you can prove it just by doing another cutting and gluing procedure. So let's do that now. So torus can be represented by a polygon with four edges and an RP2 by a polygon with two edges. So the connected sum can be represented by 6 edges with the correct edge identifications. So I'll do this. So the top part is the torus. This is the torus because opposite edges are getting glued with no twist. And this is an RP2. It's 2 edges glued with a twist. And so this is their connected sum. It's hexagon. And so what we'd like to do is get from this to a hexagon, which is a bunch of RP2s. Three copies of RP2s glued with these twists. And so here you can see each of these is an RP2 connected sum. People have asked, does it matter like what order we do these connected sums? And it turns out it doesn't. So I tend to go clockwise around my polygon, and I just draw all the edge identifications of the first RP2, then the second, then the third, etc. Okay. So how are we going to show that these two are topologically equivalent? Well, there's many. I mean, people have asked, and if you don't have any ideas, the first thing you would do is just, I guess, try random cuts. You could cut there, you could cut there. There's lots of different cuts you could do, right? But let's try to be a little more strategic. So if I just do a cut like this, that's only separating torus edges from the rest of the stuff, then in some sense, here's the boundary of the connected sum between the torus and the RP2. What this purple cut is doing is it's just cutting up the torus. And so if I glue this back, over here, all I've done is I've affected the torus, which is not really going to help me because there's no way to reduce the torus to something else. The torus is the torus. It's as simple as it can be. And so if I only do a cut that involves separating off torus edges, what I get when I reglue is still just going to be a torus connected sum with RP2. So really what I want to do is make a cut that really involves edges of the torus and the RP2. So for instance, something like that, because I'm separating now edges of the RP2 and the torus from the rest, or that, or that. Those are kind of my three options. The left cut and the right cut are more or less the same, just because of the symmetry of this picture. So I really only have two options that are really good ideas. These are the two. I'd say it's likely that either would work, but when I was solving this, I happened to do this cut down the middle. So we'll just do that. Okay. And now there's different ways you can glue things together. I could glue red to red, or blue to blue, or green to green. What I'm going to do, and again, there's probably many ways to make this work, but what I'm going to do is glue the green edges together. So if I do that, here's the right piece, and I want to glue the left piece to it. And there's going to be a flip involved. I have to flip this piece over so that the green arrows can be lined up with each other. And so if I do that, it ends up looking like this. Let's see here. So that's there. That's there. And that's there. It looks like. Okay. And now we only care about topological equivalence. So I am allowed to stretch this. So I'm going to stretch it just to get another hexagon. And then I have that, that, and that, hopefully. Hopefully I haven't made a mistake here. Let's see. I think I have made a mistake, actually. I forgot to flip the red arrow. So this should have been pointing down, which means this should have been pointed counterclockwise. Now I think it should be correct. Okay. And now, it's still not in any recognizable form. It doesn't obviously look like a connected sum of RP2s or of Klein-Bottle on RP2. So I'm going to need to do more moves. Okay. So again, let me tell you a little bit of my thinking here about what to do next. Now I'm kind of looking back at these moves because I know these are all sort of good ideas, and 2 and 3 don't apply. I don't see either of those situations in this hexagon here, but 1 certainly does. Actually, it applies a lot because I've got 3 pairs of edges, each of which is glued with a twist. So I would like to do move 1 to get those edges adjacent to each other. But there's definitely a wrong choice of what I could do next, and that is I don't really want to make this cut here. Why? Well, that, up to stretching, that's exactly the cut I just made. So if I do that cut and glue the purples together, I'm going to end up right back where I started. I'm just undoing what I did before. And also by the symmetry of this picture, this cut and gluing the purples together is also not going to work. So in terms of these moves, I make a cut from the bottom of one of the edges to the top of the other, where those 2 edges are the ones that I'm going to glue together. I don't want to use the purple edges for that because that's going to take me back where I started. So let's just use the red edges. They're glued with a twist, and the rule tells me I want to make the cut, do it this way, from, so the cut goes from the bottom of one to the bottom of the other, or the top of one to the top of the other. Here I chose the top. So I'm going from the top of the red to the top of the other red. And so I'm going to separate these 2 pieces and then glue the reds together. And so if I do that, I get this figure. And the other one I have to flip over to glue the reds together again. So I stretch it a little bit, and let's see. So this red arrow, the purple's pointing away from the bottom of it. So the purple's pointing away from the bottom of the red, and then the pink's pointing towards the top of the purple and away from the top of the red, towards the top of the purple, away from the top of the red. So this is the picture I have. And then again, I can stretch it to get another hexagon. So now I have this picture. Looks like that. Okay, and so this is great. We see one RP2 here being connected some with something else. And what is this something else? Well, this something else has 2 opposite edges being glued with no twist and 2 opposite edges being glued with a twist. That's exactly the Klein-Bottle. And so this is clearly RP2 connected some with the Klein-Bottle. Okay. But then, just let me continue this just to show how we get RP2s. So how we get these 3 RP2s here. Well, that requires more steps. Now I can start using my moves from above again. So again, it's move 1 that's going to be relevant here because I see these 2 edges being glued with a twist. And so I can do a cut and glue to make them adjacent. And so what is the cut? Well, it's from the bottom of one blue arrow to the bottom of the other. And then I glue them along the blue arrows. And what do I get? So then when I glue the other piece along the blue arrows, so purple is pointing towards blue, and the orange is pointed away from the tail of blue, so I get that. And now we're done. So I stretch this to a regular hexagon, and you can see that I've got 3 pairs of adjacent edges being glued, each with a twist. And so this is what we wanted. This is the connected sum of 3 RP2s. Okay, and so that kind of is the last move that we need, which is whenever you see a torus connected sum with RP2, you can always just replace it with 3 RP2s. And these 4 moves together allow you to reduce any polygon with any edge identifications to one of these types. Okay, and this also answers the homework question. Let me do one more example. Just, I guess I wrote 2 more examples here, but let me start with one more, just so we can get practice with this second move here, which is a little more involved. So okay, I'm just going to give myself the hardest example. So I have a list of examples here, and I'm just going to do the hardest one, which kind of shows all the different things that we might need. So let's see here. So I just chose this kind of randomly, but an octagon is kind of almost the limit of what I would want to do by hand. Okay. So here is just this random polygon with edge identifications. How are we going to figure out what surface it's topologically equivalent to from our classification? So it's not completely random. I chose this example to show you how to do move 2. So I want to emphasize that. So we've got these 4 edges, which look like a torus. It's opposite pairs being glued with no twists. The only problem is there's things in between, so we need to do moves to make it adjacent. Okay, and so let me remind you what that move looked like. So I'm focused on the green and the blue arrows, and the first cut we did to start getting these things adjacent was cut from the top to the top of one of the pairs. So like that. And then I glue the green to the green in this case. So if I cut from blue to blue, then I glue green to green. That was the first part of this move. And so let's see if I can do this. Okay, so it looks like that. After I'm done, oops. Okay. Sorry. I guess I have to redo this. So let me move it back. There we go. So these are equal. And now I'm just going to make it an octagon again. So I'm just stretching it out here. According to the... So I'm keeping the arrow order and directions the same. Just turning it back into a regular octagon. Okay, so that's my picture. And the cut I made created this new edge, which was purple. And so I've kind of replaced the green arrows with the purple arrows. And so I'm still trying to create this torus. And now I have the blue and the purple arrows to focus on. And the second move, so there's one more step to actually get these to be all adjacent to each other. And let me remind myself what that was. So I think what I want to do next, these purples aren't adjacent. So I'm going to do a cut and glue to glue them together. It's a good color, pink. Okay, so that's my second cut, and the blues are kind of already in the correct relative position for the torus, but the purples aren't, because I have this other edge that's kind of in the way. And so I'm going to cut so that I can glue the purples together. So I either have to go from the tail of one purple to the tail of the other, or from the head of one purple to the head of the other. I'm going from tail to tail. And I'm going to glue this piece on along the... I guess I have to glue along the blue edge here. Sorry, I said I was going to glue the purples together, but obviously can't do that with this cut. But I can glue the blues together. And now we're in good shape, because if I turn this back into an octagon by stretching it, you can see that these pink and purple arrows look like a torus. So this gets stretched to a regular octagon. The purples are being glued with no twist. The pinks are being glued with no twist. And I've got, let's see, then I've got the reds both being glued with a twist, and the oranges both being glued with a twist. So this is my new picture. Okay, and now I can split it like this, and I can see that the left-hand side is coming from a connected sum of a torus, and the right-hand side, as you might guess, this is going to be connected sum of two RP2s, but we haven't yet gotten it into that form. So now I'm going to do move 1 with these RP2s. So let's first focus on the red ones. So I can cut this off. And I'm going to glue the red edges together. And there's a twist involved, so, oops. So I have to be a little careful. So this green arrow is pointed towards the tail of the red. So it's right there. And the orange arrow is pointed towards the tail of the green. So it's like that. Yeah, that looks right. And again, I always turn it back into a regular octagon by stretching. And this is my picture. So now I've kind of got three chunks, which are recognizable. I've got the torus on the left, I've got the RP2 on the upper right, and then I've got this thing here, right? Now there's two ways to deal with this. One is you could just sort of notice that this can be stretched. So I could stretch this into, basically if I shrink this angle, if I pull this vertex in and shrink this angle down to 0, I can just glue these two orange edges together without any twisting at all. So this can be stretched to something that looks like this. Oops. Let's see here. So if I shrink those orange edges in together, then that happens right here. The orange edges get glued together. I guess they'd be pointing outwards. And so I can stretch this octagon enough until I can glue these two orange edges together, which turns it into a hexagon. And so now I just have something that I'm familiar with. You know, this is just a torus connected sum with an RP2, which, as we know, is the same. I should always use this symbol, topologically equivalent, same up to stretching as 3 RP2s. Another way to deal with this last part is you can see that these are two arrows. Oops. These are two arrows which are being glued with no twisting. And if I label this whole part as X and just label this vertex as Y, then this falls into the setting of move number 3, where I've got two edges being glued without a twist. And between these edges, on the left side, X has edges, Y has edges, but none of the edges of X are being glued to the edges of Y. That's the situation we're in here, except that Y just happens to have 0 edges. It's just a point. But still, we can use that rule, and what the rule says is basically you can just delete those arrows. And so if we do that, we're left with just the hexagon, like we had here. Okay, so you can either just see that this can be stretched in so I can glue those orange edges together and remove them, or you can call upon move number 3 that we had available to just delete those edges, because this is a special case of that situation. Okay, so yeah, I wanted to do a kind of involved example. This one used all of the moves that we have available to us to show you kind of how this works in practice. All right, thanks.